This is part 2 of 3 tutorials on magnetic nanoparticles. We hope to put these up somewhere publicly available, so hopefully you're watching it somewhere easily accessible. And today we're going to talk about magnetic nanoparticle dynamics. Okay, if I can get my slides to change. So firstly, why study dynamics? And I should say that what I mean by dynamics is any change that happens as a function of time. And the reason for me why we would study dynamics is because most applications of magnetic nanoparticles rely on their magnetic or physical response to an external stimulus over time. Okay, so let me give just 2 examples. There's more examples than this, but just let me give 2 examples to make this idea concrete. My first example is drug delivery. In this case, the drug delivery is through mucus, and this is a picture given to me by colleagues at University of Colorado, Colorado Springs. And here, magnetic nanoparticles are these dark gray regions, and they're being used to deliver drugs through very highly viscous mucus, or sticky snot, as I prefer to call it. And they use magnetic field gradients to drag those magnetic nanoparticles through something that otherwise is impenetrable to the drugs to deliver drugs to the underlying tissue. So that's one example, and we'll talk more about field gradients at the end of this session. Another example where we want magnetic nanoparticles to respond in time is in magnetic hyperthermia, which some people on the call have some experience with. In this case, magnetic nanoparticles, in a very simple terms, are inserted at a tumor. We apply an oscillating electromagnetic field, and that gets those particles to wiggle. And that wiggle or that jiggle is heat. And so we can heat a tumor by a couple of degrees and cause that cancer to die while keeping, hopefully, the surrounding tissue healthy. So again, we have to have this response, this jiggle in time. So I hope that gives enough motivation for why we should study dynamics. So I want to define another term that we use a lot when studying dynamics, and that's the term relaxation. So I would say that relaxation is looking at the dynamics in order to reach a steady state. All right. And we're going to be interested in 2 types of relaxation. The first one is where it's the magnetization which is relaxing. So that big M that we talked about in part 1 moves towards a steady state value as time goes on. So that's magnetization relaxation. We're going to go into this in depth. And then the second type of relaxation is physical relaxation. So this time the particle density or the microstructure, the configuration of nanoparticles physically in space moves towards some steady state. Okay, so there's 2 types of relaxation here. They might be working together, they might be occurring at the same time, but they can be decoupled as well. We can have the magnetization relaxing or the actual physical configuration of particles relaxing. So we're going to start with number 1. And I'm going to break that into 2 pieces as well, so we can try to navigate where we are in this story about dynamics and relaxation. I'm going to talk about magnetization relaxation mechanisms. There are 2 main ways in which the magnetization can relax or get to some steady state. The first way is when that macro spin moment for each nanoparticle, which we talked about last time, little m, can rotate internally in a particle. And we call this Néel relaxation. So let me give you some cartoons to explain this. And over here on the right-hand side, I've got an external applied field, which is upwards as a reference. And that's going to be driving our relaxation or driving our dynamics. So imagine we have one magnetic nanoparticle. You guys are used to seeing this cartoon from last time. And the macrospin moment defining, the single domain magnetic moment of this particle is starting roughly down. And because of this external field, we know it wants to move to up. Through Néel relaxation, that happens by that moment rotating But notice that the easy axis that we drew last time with a dashed line is not changing. So this is saying that the particle itself is not moving or not moving substantially, but inside the particle, the magnetization is moving. And so eventually we get to some direction roughly up. It's not going to be perfectly up because remember, we still have that thermal jiggle all the time affecting the direction of the macrospin moment. So this is Néel relaxation. We've got the magnetization moving and not necessarily the particles rotating. The second mechanism for magnetization relaxation is a physical rotation of the particles, as you might have guessed. And this is known as Brownian relaxation. So here we have another cartoon of a magnetic nanoparticle, and this time I've shaded it so we can see quite easily the particle moving in time. And so here are some snapshots in time again, and see the whole particle is moving, which we can see by that shading rotating and also by the easy axis moving as well. And eventually the particle ends up again with its moment pointing upwards, but this time via a different mechanism. Okay, so we're going to delve into these two mechanisms more deeply. One thing I wanted to warn you about, which I discovered far too late, is, you know, these two terms, Néel and Brownian, you'll read a lot about in the literature. You'll read about it a lot in papers. Unfortunately, one of the main contributors to understanding Néel relaxation was Brown, unfortunately. So it's quite confusing. There's this seminal paper in the 60s by Brown on Néel relaxation. And that's very unfortunate because the other relaxation mechanism is known as Brownian relaxation. I should say this Brownian relaxation is named after a biologist called Brown, who in the 1800s observed under a microscope pollen jiggling around, rotating and translating when there was apparently no external forces being applied. So this Brownian motion, or this thermal motion, is named after a biologist. Okay, so let's delve into Néel relaxation in some detail. Remember, this is the macrospin rotation. And from last time, we know that there's actually an energy barrier that needs to be surmounted going from up to down. Now, I've just drawn it very simply here. There's actually no applied field here. And so the up and the down direction have equal energies. So we have to surmount that barrier. And that barrier we talked about last time as well is smaller if the volume of the particle V is smaller. So this is a dominant relaxation method for small particles where the barrier to reversal is smaller. And so it's easier for that macrospin to surmount the barrier. The other way we can make it easier for this Néel relaxation to occur is to heat up the particles. So at high temperature, we give the particles lots of thermal fluctuations. Those thermal fluctuations are what takes us over the barrier. Now, this is a stochastic process because thermal fluctuations, you know, they have some statistics to them, but they're unpredictable. And because it's a stochastic process, we can't talk about a time for a particle to relax. We can only talk about an average time for a particle to relax via Néel relaxation. Okay, and I've got a diagram to try to explain that in more detail. So let me see. Oh, they are running. Good. So this is an animation put together by one of my former students, Artek Chelafor, who graduated in 2022. Some of these are not stopping, I don't think. Oh yeah, some of them are just restarting, but basically you can see this nanoparticle, it relaxed in 3.1 nanoseconds. This one did some crazy trajectory and relaxed in 2.3 nanoseconds. This one over here looks like it goes to about 20 and then restarts for reasons I don't understand. This one, let's see, we get to about 27 nanoseconds. So you can see everyone is doing something different. This is a stochastic process. We jiggle around, eventually we can overcome the barrier. And so, oh, and I should say these are our simulation results. And what we do is we do simulations on what's known as a thermal Landau-Lifshitz equation, okay? What we can do, and we do this for more particles than just 5, but 5 is, you know, a good number to put on a slide, is we take all of these simulations, say for a few thousand particles, and we average them, and that gives us the average time to relax. So here, for example, it was 14 nanoseconds. But I hope that captures for you that this is stochastic, but we can characterize it by saying, what is the average time to go over the barrier? Okay. All right. This is a summary slide of what you just saw with those videos. This is the net magnetization of an ensemble of 5,000 particles. And then here is time, and you'll see it's in nanoseconds here. And we started all the particles downwards, which is completely artificial. You would never see this in an experiment, but we can do it in a simulation. So all the particles are down, giving us a normalized magnetization of exactly -1. And then we see the particles all relax to the up direction because there was an external applied field. And there's actually 2 relaxations that go on here. Firstly, there's just a thermalization, where the particles magnetization or their macrospin moment is processing or jiggling around within an energy well. And then here we get a slower relaxation, which is the longer time hopping over energy barriers that we've been talking about. We can fit a curve to this graph to figure out a mean relaxation time. So for example, for this one, we get 46 nanoseconds. I guess what you can take away from this as well, which is important, is that when it's Néel relaxation, the relaxation times are on the order of nanoseconds. They're quite fast. And we can contrast that to some of our other relaxation mechanisms in the slides to come. Okay. I think this is just 1 or 2 more slides on Néel relaxation. We've talked about it depends on this barrier height, kV, where K was the anisotropy constant from last time and V is volume. And it's important to compare that barrier height to thermal energy, Boltzmann's constant multiplied by temperature. When we have any sort of dynamics which involves traveling over an energy barrier, we can write down the time or the average time for that relaxation according to this, what's known as an Arrhenius relationship. So this is the relaxation time. I'll call it tau sub n for Néel relaxation time. And it's given by some constant tau naught, which people often call the attempt time. And then it's an exponential, and we see that competition between the anisotropy barrier and the thermal energy arising here. I think this might be one of our first equations that we've come across in our 1.5 lectorials so far. So I hope you'll forgive me for an equation. There are a couple more. I'm trying to take the equations out, but this one's important because we see it a lot of times. Okay. All right, let's move on to Brownian relaxation, which you may remember from about 5-10 minutes ago is the whole particle rotating. Obviously, the particles have to be in a fluid for that to happen. If they're frozen into a matrix, the particle can't physically rotate, but in a fluid, they can. This is typically the relaxation mechanism which dominates for larger particles. Then the Néel relaxation is suppressed and Brownian takes over, or lower temperatures. So remember, lower temperatures, the particles become blocked. The anisotropy barrier is just too large to surmount. And so in that case, Brownian may be the only relaxation mechanism that's available to the particles. Again, another equation, but this one's quite simple and sweet. This is the average time for a particle to relax in a fluid via this Brownian mechanism. So I've called it tau sub B. And it depends on the fluid viscosity, which is eta, It depends on the hydrodynamic volume of the particle, how big the particle is, V sub h. And again, thermal energy is in there because it's thermal fluctuations which limits how quickly this particle can rotate. I've got a reference here to an old book by Frenkel, 1955, but it's actually the book that I've used to see this derived is one by Debye, which was an even earlier book. I think it's available online, but you can derive this by looking at stochastic differential equations for these particles relaxing. I know you're all going to go out there and read the book, and it's a real page turner, but that's where this comes from. Okay, and it sort of makes sense. If we have a more viscous fluid, a more sticky fluid, it should take longer for this particle to rotate. I mean, we know that from our own lived experience. So, and we see that. So if viscosity is bigger, we have a longer time to relax. Conversely, if we have higher temperature, it's quicker to relax because it's got more jiggle, it's got more motion at higher temperature, and so it can relax into its average direction much faster. Okay, let's see some Brownian relaxation in action. This is again a simulation done, I think this one was by me, not even by a student. And so we have a particle again pointing with its moment pointing downwards. This particle has a radius of 10 nanometers, and I believe it's magnetite or based off magnetite. You might also see, you can tell me if you can see it, there's a very fine red line on top of that black arrow. That's the easy axis of the particle. So we may see that the moment the black arrow comes away from that easy axis, we'll see. What I'm going to do is I'm going to press play, and we're going to see roughly how long it takes this particle to relax to the upwards direction in a field of 20 millitesla. So everyone, you know, chime in with your answers. We'll have a look. So there it goes. We do see a little bit of the moment coming off the easy axis. The video goes for about 100 microseconds, which is good because it's about to head out of frame. How long do you think it took? I mean, it's an estimate, but how long do you think it took to relax in that field? Anyone want to chime in? Should I play it again while you're thinking?
10 microseconds.
Yeah, I think, yeah. I mean, it's a hard one to quantify, isn't it? Because, you know, it gets upwards and then it keeps jiggling around. So it's very hard to quantify unless you have an ensemble, I must admit. But I would say 10 or 20 microseconds is what we notice. Now, the first thing to note is, how does that compare to the Néel relaxation times we were talking about just before? Can anyone, what time scale were we on before?
We were in nanoseconds.
We were on nanoseconds, and now we're in microseconds. So I hope that's good evidence for you that this Brownian relaxation takes a lot longer on average than the Néel relaxation, depending on the particle. We'll talk about that in a second, but this is typically a longer time to relax. Notice as well that we're mainly interested in the rotation of the particle, but you saw that there were Brownian translations as well. This particle was moving here, there, and everywhere via Brownian motion. So it's not just the rotations that are thermal, there's translations in the fluid as well. Okay, this is my ever popular aside on units. We talked about units some last time when we made sure we all knew the units for magnetic moment, magnetization, field, and so on. But I just want to make it really clear, because units in the area of magnetism research is a continuous pain for everyone, okay? So I'm going to try, I think there's one instance, you might try to spot it, but I'm going to try wherever possible to use SI units, but many papers still are written in centimeter gram second or CGS units, okay? I don't have a strong preference either way, but it seems that the trend is that we're heading towards SI units, which is probably the correct way to go. So just going back to last time, we talked about units, as I said. I want to remind you that magnetic field, the H field, has units of amps per meter. And magnetic induction, a B field, has units of Tesla. And in a vacuum, it's very easy to convert from magnetic induction to magnetic field. There's a proportion, a constant of proportionality, mu naught, which is the vacuum permeability or the permeability of free space. Okay, so those are our two units when we're looking at field. And to give you a feeling for how big this is, because that's all very nice, but I know from my own experience, it's nice to know how big these fields are. So 20 millitesla, 200 Ersteds in the old language. 20 millitesla is about 1.6 times 10 to the 4 amps per meter. And how big is that? It's about 400 times larger than the Earth's magnetic field in London. I chose London because these talks were originally given in London. It's on that order elsewhere as well on Earth. So 400 times bigger than the Earth's magnetic field, which is probably good because if we're applying this to magnetic samples and expecting a response, it makes sense that it's larger than the Earth's magnetic field, because otherwise the Earth's magnetic field would be, you know, causing havoc in all our devices everywhere. So good. It's much larger than the Earth's magnetic field, but it is much smaller than, say, the field that is used in an MRI, magnetic resonance imaging machine. So an estimate of 100 times smaller, depending on your MRI. So we're sort of in between. We're not a massive field that you would generate in a hospital, but we're much larger than, say, the Earth's magnetic field, which is around us all the time. And another note is this is insufficient to dominate Brownian rotation. So it's sort of it's a mild field in terms of influencing our relaxation mechanisms. All right. The volume magnetization has this units of amps per meter that we talked about last time, but you also see people talk about mass magnetization as well, which is total magnetic moment per unit mass rather than per unit volume that we were using last time exclusively. And so the SI units for mass magnetization is amps meter squared per kilogram. Again, you'll read a lot EMUs per gram, which is the CGS unit for that. And there are ways of converting, but, you know, we don't want to spend our whole life doing conversions, even though that's where we are at. All right, let's leave units and go back to magnetic relaxation after that little diversion. And what I want to do now is combine the two mechanisms, because you can imagine that for particles, especially of some intermediate size, we can have some internal magnetic relaxation and we can have some external rotation both. If you have two processes, two relaxation mechanisms happening at once, you can imagine that the faster one is more important. Okay, the one that happens first is more important to you. I think, again, that sort of resonates with our lived experience, you know. If the train doesn't come for 12 hours, but the bus comes in 3 minutes, the bus is more important to me. That is my travel time, okay? And so that, I think, helps explain this formula here, which says that our total relaxation time, tau, is a combination of the Néel relaxation time, tau sub n, and the Brownian relaxation time, tau sub b, but we add them reciprocally. And the reason why we do that is because this gives the faster process the dominant contribution to the total relaxation time. Okay, so the smaller process will have the bigger term on this right-hand side. So let's plot it. Let's actually plot the two expressions I gave you earlier for Néel relaxation and Brownian relaxation. I'm going to put on a plot as a function of particle size. Okay, so let me explain what's going on here. This is particle diameter on the horizontal axis, and this is some characteristic time in seconds on the y-axis. And you'll notice it's a logarithmic scale. So we're going through 5 orders of magnitude here. And the blue line is our Néel relaxation time. This takes off because, remember, it depended on an exponential of the volume. So this just diverges as our particle diameter gets bigger. And then the orange is our Brownian relaxation time. You might remember that just scaled with the volume or the hydrodynamic volume. So that is a little bit less steep in how it varies as the particle diameter increases. And then the red line, which you can just see poking out here, this is our total relaxation time. And it goes from being Néel dominated to Brownian dominated. And there's this region here where both mechanisms are playing a role. Okay, so we have this crossover regime. So I think this plot's really useful for understanding small particles. We've got Néel relaxation dominated, big ones it's Brownian, and in between we can have a crossover effect. Okay, this is all assuming we have zero field, which is actually an issue that we're trying to look at, is what happens when we put a field on, and these relaxation times can change markedly. Okay, that's it for magnetization relaxation. Let's switch over to now physical relaxation of particle microstructure. Okay. All right. Now, what's key to understanding this is that when I have a macrospin, it feels a force due to the presence of magnetic field gradients. So here I've just got a bar magnet with uniform magnetic moments pointing up. So it's a ferromagnetic bar magnet, everything's uniform. And this is the field that's predicted from that bar magnet. If I put a macrospin up here, there's no field gradient or very little field gradient, so not much will happen to it. But if I can be, say, down near these corners where the field is really changing its direction and its magnitude quite strongly, that's where I'm going to have a large force. So to understand where there are field gradients, you've just got to think that these field lines need to be changing their density quite strongly. So as I said, this is at the edges, we have a strong gradient. If I could make a magnet that has, say, a tip, then I generate a strong gradient at the tip, which can be useful. And we can use this for all sorts of applications. Here's one that's close to my heart because it's work that I have done together with Mus Crawford at University of South Carolina. We can imagine generating large field gradients. For example, look at this substrate that has North Pole, South Pole, North Pole, South Pole, North Pole, and so on. There's large field gradients in between those transitions. And so those field gradients cause particles to be attracted down to the surface. And we can self-assemble particles. Here they're just in lines, but we can imagine creating any shape we want as long as we can template the stray field how we want. Okay, so we can use this, for example, for self-assembly. Here's a simulation of that happening rather than a static diagram of this happening. This was made by another student of mine at University of Colorado, Jonathan Davidson. And I've put underneath what actually the magnetization is at the bottom of this volume that you can see. So there's two regions where the magnetization is down. And then there's a region in the middle where the magnetization of the substrate is up. And here's one for the audience. It's an easy question, I hope. Where do you think all these magnetic nanoparticles, which are the red spheres, where do you think they're going to go as I press start on the simulation?
At the interfaces?
Yeah, these transitions between the up and the down. Very good.
And would those be the same as domain boundaries?
Yeah, so they're not quite the same as domain boundaries because they're really dominated by grains. It's not a traditional domain wall, but yes, magnetically it looks very similar to a domain wall. Good. And then imagine it extends backwards through this volume. I've only drawn it at the front for simplicity, but these stripes go all the way back through the volume. So let's press start. And we can see all the nanoparticles. You see that thermal jiggle again we talked about? They're translating and rotating thermally in the fluid, but the gradient is pulling them down. And so we see the microstructure relaxes. We get those two stripes. And you might even notice it seems like the particles make sort of a hexagonal closed pack arrangement. It's sort of hexagonal in some way. There seems to be some ordering even within the stripes. Okay, good. All right. Oh, and then it's playing again. This picture of magnetic nanoparticles being attracted or feeling forces due to magnetic field gradients is complicated again by dipolar interactions. We saw this picture last time and sort of threw up our hands and went, wow, this is difficult to deal with. Again, we get gradients, magnetic field gradients generated by one particle, which therefore puts a force on neighboring particles. So we can expect particles not just to assemble because of an external field, but also to assemble because of fields that they feel from their neighbors. So they could even self-assemble without a field. The presence of a static or oscillating applied field but can aid that self-assembly though. And there's lots of papers now showing that static fields and even AC fields will aid the zippering together of particles. And quite often they form chains, which we'll see in the next slide. So here's another simulation. This one again is from my group, from a former postdoc, Nick Anderson. And these are larger particles. These are 25 nanometer radius particles. So they're really on the borderline of being single domain, but anyhow. So they're big particles and they're in an oscillating field. We start them at random configurations, and then we're going to see what they do because of the interactions they feel from each other and from the interaction they feel with this oscillating field, which is going to be up and down in this picture. So let's press play and see what happens. So they're jiggling around. They're all pointing upwards because of the field. Then they flip to downwards. Let's see another flip upwards now. So they're following the field, but at the same time, you can see that they're moving closer together because of those dipolar forces. So we get chains formed. We get some sort of more odd looking chains. This one here, for example, is like a fatter chain. It's 2 particles long. A lot of them are single particle chains, which happens when we've got a large field. If we have a weaker field, they can be kind of more messy, less ordered. So we see that chaining occurring, which is a combination of there being an external field and them interacting with each other. Okay. See if I can go to the next slide. Apparently not. Oh, I'll have to watch it forever. Okay. One more thing to say about these dipolar interactions and the physical microstructure is that this in turn can affect the magnetic relaxation we were talking about earlier. So this is the video you've all seen, you've all analyzed, you've all did an experiment. Everyone said, oh, about 10, 20 microseconds for relaxation for this single particle in a fluid. What I want to do is contrast that to the same particle being part of a small chain. Okay. So let's see, here's the same particle as part of a small chain. Again, it's a little bit artificial because we started it in like a perfect chain of 5 particles and they're all pointing down. We're going to run the same sort of video. We're going to see what happens as we play the video on the order of microseconds. But this time there's a different physical structure, a different microstructure for the particles. And I want you to all tell me how long it takes to relax this time. Okay, everyone ready? No one moved. Is everyone ready? There was some motion. Good, excellent. Okay, you're still awake. All right, they're jiggling. Their perfect chain order has really been disrupted by the thermal fluctuations. Now, I stopped doing the simulation at 100 microseconds because I thought we'd be done, unfortunately. But you can see the relaxation still hasn't occurred, has it? They're not pointing upwards yet along the field direction. They will eventually get there, and I apologize for not running the simulation long enough. You can see the ones at the ends that actually have less neighbors. They're on their way. They're sort of, halfway there. But the ones in the middle are like, no, I'm much more influenced by my neighbors than this external field. So in this case, the Brownian relaxation time has been greatly extended because of a changed physical structure of the magnetic nanoparticles, this presence of a chain. Okay, so let's summarize. I've gone on long enough. We've talked about magnetization relaxation, which is when the magnetization M of an ensemble of nanoparticles reaches some steady state value due to Brownian or Néel mechanisms or a combination of both. And then we've talked about physical relaxation, where the particle density moves towards a steady state. And the key to understanding that is to understand the presence of magnetic field gradients, whether it's external field gradients or field gradients from neighboring particles. One thing I want to hammer home, which I think I've already mentioned, is that the relaxation times go over 10 orders of magnitude. So we were looking at nanosecond relaxation for some particles due to Néel relaxation, and the self-assembly that we see can take on the order of minutes. Okay, and this poses a real problem. I mean, you may have no sympathy at all. I think most of you are experimentalists, but for theorists, this poses a huge problem because we're trying to understand processes occurring on the nanoscale all the way through to minutes long. And to bridge that gap is really a difficult problem while keeping the physics intact. All right, let me talk about implications. And this is really a segue to next time. The hypothermia example that I started with, we want to maximize the energy produced. We want to maximize the heat produced from an oscillating field. And understanding the magnetic relaxation time really helps us do that. So I've drawn two plots. These are my sort of made up plots. They're not real data, but I've got an oscillating field, which is the solid line. And then I've got the magnetization following that field. There's sort of a little lag, but the magnetization's following. Versus over here, notice the magnetization switches very quickly. And then the particles are just hanging out and waiting till the field switches again. For heating, this side on the left, this is our better scenario because the field is always doing work on the magnetic particles. Whereas over here, we spend a lot of our life waiting. So the energy, or I guess the power we're producing, is less. So understanding the relaxation time helps us to actually design materials to optimize our applications. One more example is to talk about dynamic magnetic susceptibility measurements, which hopefully we'll talk about a little bit more next time. These measurements really are interested in seeing how the magnetization again keeps up with an oscillating field. And so here I've got the component of the magnetization, which is in phase with an applied field, as a function of applied field frequency. And again, it's a logarithmic scale. So I'm visiting magnetic field frequencies that change over orders of magnitude. Oh, that one's wrong. That can't be the same. I think that should be a 7 there. And what happens when we're at low frequency, the magnetic nanoparticles can keep up with the oscillating field. So think back to our videos, the little moments can keep up with the field. And then when the field becomes too fast, it cannot keep up anymore. And now there is no part of the magnetization which is in phase with the field. So again, if we want to interpret these measurements, which we can make in the lab well, we need to understand what the relaxation time is and how we can then reverse engineer and understand how those relaxation times tell us about the nanoscale energy barriers in a system. And as I said, this is really a segue to next time, where we are just going to be talking about characterization measurements exclusively. So I'll leave it there. That's our end of part 2. Thank you for joining me and hanging out again. And hopefully we'll finish on a high next time for part 3 on characterization.